Students will be able to find the position and acceleration of a particle given an equation in parametric form. The particle moves on the curve y equals x squared, so the x component has velocity of 3t minus 1, and for t greater than or equals 0, at time t equals 0, the particle is at 0.24. At time t equals 2, the particle is at what point? So let's get the x position, which is starting at 2 when t is 0. So we'll go 2 plus integral from 0 to t equals 2. And the x prime is 3t minus 1. So that's 2 plus, that integral of that is 3 halves, t squared minus t. And that's from 0 to 2. So 2 plus, and then 4 divided by 2 is 2. 2 times 3 is 6, minus 2, and then minus 0 and 0. So that's going to be 2 plus 4 is 6. Well, now we have to find what point that is, and we got the x. It's 6 comma something, but we know that y is equal to x squared, so 36. Particle moves in the xy plane, so at any time t, its coordinates are that. At t equals 1, what is the acceleration vector? Well, the velocity vector is 3 comma 3t squared minus 2t. And the acceleration vector is 0, 6t minus 2. We're evaluating that when t is equal to 1. So 1 comma 6 minus 2 is 4. Oh, no, excuse me. 0, 4, not 1, 4. The particle moves along the curve. If x is 1 and dy dt is 2, what is the value of dx dt? So let's take the derivative. First times the derivative of the second plus the second times the derivative of the first with respect to t is equal to 0. So we know x is 1, 2 times 1. They tell us dy dt is 2. We don't know y, but 2 times 1 times y is equal to 8. Y is equal to 4. So 4 times 2 times dx dt is equal to 0. So 8 dx dt is equal to negative 4. So dx dt is equal to negative 1/2. Use a calculator. An object moving along a curve in the xy plane has position xt, yt. At time t with dy dt as that, at t equals 5, the object is at the point 37. Find the y coordinate of the position at time t equals 1. Well, we could write that the position at time 1 plus the displacement from 1 to 5 is equal to the position at 5. So what do we want? We want the position at 1. So the position at 1 should be the position at 5 minus the displacement from 1 to 5. In other words, we're backing up. So instead of adding the displacement, we're going to minus the displacement. Well, the position at 5, they tell us is 3, 7. So 7 minus the integral from 1 to 5 of 3 plus cosine of t dt. We're going to plug that into our calculator. You get negative 3.199. We're going to use a calculator for these. For t greater than or equal to 0, a particle is moving along a curve. So its position at time t is x of t, y of t. At time t equals 1, the particle is at position 2, 6. It is known that we have those derivatives. Is the movement of the particle left or right at time t equals 1? So dx dt evaluated when t is equal to 1 is 1 minus 3 over e to the 1. So it's a negative 2 over e. That's negative, so moving to the left. Find the slope of the path of the particle at time t equals 1. So dy dx is equal to at 1 is tangent of 1 over 1 minus 3 over e. Over e. How come I can't write an e? There we go. Which is equal to, if we plug that in the calculator, we get negative 2.117. Find the speed of the particle at time t equals 1. So the speed is a magnitude of the velocity vector. So we have the square root of 1 minus 3 over e squared plus tangent squared of 1. Throw that in the calculator, get 1.722. An acceleration vector of the particle at time t equals 1. Well, we're going to use math number 8, which is derivative. So I'll just tell you that acceleration is 1.104 when we plug in the calculator and 3.426. And the key is use math number 8 on the calculator, and you got it. From the x-coordinate of the particle's position at time t equals 5. Well, we know where it is at 1. So we have 1 plus integral from 1 to 5 of, let's see, what do we find? The x-coordinate. So that's going to be t minus 3 over e to the t dt. No, not 1. Where'd I get 1 from? 2 right there. 2 plus that, which is 1.612. Right, but do not evaluate expression to find the distance traveled by the particle from time t equals 3 to t equals 6. So integral from 3 to 6 of the square root of t minus 3 over e to the t squared plus tangent squared t dt. Point P moves in the xy plane in such a way that there's the derivative of x and the derivative of y. For t greater than or equal to 0. Find the coordinates of P in terms of t, given that t is 1, right? X is the natural log of 2, and y is equal to 0. Find the coordinates of P. Well, we know the derivative. So the x-coordinate, the position, is the integral of 1 over 1 plus, or t plus 1 dt. So x is the natural log of the absolute value of t plus 1, but then plus c. But they tell us that when t is 1, x is the natural log of 2. So natural log of 2 is equal to the natural log of, well, 1 plus 1 is 2 plus c. So in other words, c is equal to 0. So the x-coordinate is natural log absolute value of t plus 1. Y is equal to the integral of 2t dt. So y is equal to t squared plus c. Let's say that when t is 1, y is 0. So 0 is equal to 1 squared plus c. So c is equal to negative 1. So y is equal to t squared minus 1. Find the coordinates of t given that t equals 1. So when t equals 1, we got the natural log. Oh, in terms of t. Oh, we got it. So the point is x, no, let's do this. Natural log absolute value of t plus 1, comma, t squared minus 1. There's the point in terms of t. Write an equation expressing y in terms of t. So if we take this right here and get it into exponential form, we have t plus 1 is equal to e to the x. So t is equal to e to the x minus 1. Now we're going to plug that in for this right here. So we have y is equal to e to the x minus 1 squared minus 1. Find the average rate of change of y with respect to x as t varies from 0 to 4. So we need y of something minus y of something over something minus something. Well, we need all these x values. X value for 0, if we go up here, is a natural log of 1, which is 0. All right, so for 0, x is 0. For 4, x is the natural log of 5 by plugging it in right there. So we need y of natural log of 5 minus y of 0 over natural log of 5 minus 0. But we have the y equals with respect to x right there. There it is. So we plug natural log of 5 into this. E to the natural log of 5 is 5. So 5 minus 1 is 4 squared minus 1. If we plug 0 into this, we get 1 minus 1. So we get plus 1 minus negative 1 over natural log of 5. So we get 16 over natural log of 5. Find the instantaneous rate of change of y with respect to x when t is equal to 1. Well, that's another way to say what's the derivative. What's the derivative when t is equal to 1? So the instantaneous rate of change, or dy dx, is equal to 2t over 1 plus t. We're just evaluating that when t is equal to 1. So we get 2 over 1 over 2, which is 4. And here's some review. Here's some old stuff. We're going to let f of x equal 1 plus 3 e to the x to the 1 over x. Oh, no, by the way, this is infinity to the 0. So we have the natural log f of x is equal to 1 over x natural log of 1 plus 3e to the x. And then we introduce the limit into this. Limit as x approaches infinity, natural log f of x is equal to limit as x approaches infinity of natural log of 1 plus 3e to the x over x. So now we can do L'Hopital's, which is 1 over 1 plus 3e to the x times 3e to the x. Oh, and I need limit as x approaches infinity. Well, this is ending behavior. So as x approaches infinity, this 1 right here becomes insignificant very quickly. So this is equal to, it's really equal to, it acts like 3e to the x over 3e to the x, because the 1 becomes very insignificant. So 1, and the answer is e to the first. Here we have the limit as a approaches infinity, integral from 3 to a of x to the negative 3 dx. So we're going to add 1 to the power. That's negative 2 times negative 1/2. We have limit as a approaches infinity of negative 1 over 2x squared plus, no, here we have this, from 3 to a. So we have limit as a approaches infinity of negative 1 over 2a squared plus 1 over 2 times 9. So it ends up being 1 over 18.